So in cryptography, what happens is there is an encryption algorithm. Encryption algorithm is used to encrypt a plain text into ciphertext. Ciphertext is readable, but when you read, it doesn't make any sense. So normally we call it as gibberish. Gibberish means you can still read, but it won't make any sense. Okay? So there is an algorithm called as encryption algorithm that encrypts the plain text to ciphertext, and this is parameterized by a key. Parameterized by a key means it is enabled, this encryption process is enabled by a key. Okay? And the ciphertext is sent to the receiving side, and at the receiving side, the decryption algorithm, with the help of the decryption key, it actually deciphers, that is, converts the ciphertext to plain text. Okay? So there are two different types of, two broad categories of crypto algorithms. Okay? Symmetric cipher or symmetric key crypto algorithm, and asymmetric key crypto algorithm or asymmetric ciphers. So asymmetric crypto algorithms are also called as public key crypto algorithms. So you will come to understand shortly why we call the asymmetric crypto algorithms as public key crypto algorithms. Okay? So what is meant by symmetric key crypto algorithm? Symmetric key crypto algorithm means the encryption key and the decryption key is the same. Same key is used for encryption as well as decryption. So what happens is there is a vulnerability here, a weakness here. So what is the weakness in the sense? The sender, when he or she sends the ciphertext, have to send the key as well, because the same key is used for encryption as well as decryption. So if there is an adversary, and adversary means a person who has malicious intention, okay, intercepts the network, enters the network, and sniffs the ciphertext. So when an adversary, okay, intercepts the network and reads the ciphertext, he or she will be able to read the key as well, because the key is also sent along with the message in symmetric key cryptography. Symmetric key cryptography means the same key is used for encryption as well as decryption. Okay? So along with the ciphertext, key also sent. So if an intermediary or adversary with malicious intention sniffs the network, he or she will be able to read the ciphertext as well as the key. It is as if you are locking with a padlock and leaving the key mistakenly or forgottenly in the lock itself. Okay? So that is the vulnerability here. So to overcome this vulnerability, what people do is, they use different channel. So in one channel, they send the ciphertext. In another channel, they send the key. Okay? Today, we use different algorithms as well. For example, we send the ciphertext using one algorithm, maybe RSA, and we send the key, through another algorithm, for example, Diffie-Hellman. RSA may not be the right example because RSA is asymmetric key cryptography, public key cryptography. Okay? And there also Diffie-Hellman is used to exchange the keys. It's a different story. Okay? Yeah, that is symmetric key cryptography. Yeah? When we say asymmetric key cryptography, for the encryption, different key is used, and for decryption, different key is used. Okay? So we are going to have a pair of keys. Okay? So this pair of keys is called as public-private key pair. So you may ask, why then this algorithm is not called as public-private key algorithm? It is simply called as public key cryptography or public key algorithm. It's just by practice. We have been calling it so from day one. So it is simply called as public key cryptography. When we say public key cryptography, we actually mean public-private key cryptography, which is actually asymmetric key cryptography. Okay, two keys are used. So usually the keys are pair. So when I explain RSA, I will tell you why the keys are called as a pair. Called as a pair means the public-private key is actually tied. Tied means not tied to the rope. It is tied means they are interconnected through a mathematical relationship. Okay. So when I say this is the public key and this is the private key, this public key will work only with this private key. Okay. This public key will not work with another private key of a public key pair. If I have a public key pair here, two pairs of keys, asymmetric key cryptography or public key cryptography, this public key will not work with this private key. That's why this is called as a pair. And that's one of the learning exercise for you in your assignment 3. So where to go and get this public private key pair? Am I supposed to purchase from somewhere? That's why we have central authorities. We call it as CAs. Okay? And in Malaysia, we have 5 or 6 organizations who have been authorized by the MCMC, okay, Malaysian Commission for Multimedia and Communication, okay, that operates under MOSTI, Ministry of Science, Technology, Innovation. So they are authorized, to say who are the CAs who can issue the public-private key pair. Okay. So in your essay, some of you emailed and asked me, should I just list the names of the 5 entities or 5 organizations which are authorized to issue or sell the public-private key pairs? Just list them is good enough. No need to write stories about them. Okay. This is a learning exercise to know who are the entities, who are the organizations in Malaysia who are authorized to issue this public-private key pair. Okay. One of them, very simple. That's the beauty of the bureaucrats here, or the government officials here, including the government. One of the organization entity is your post office or your postal adju. Okay, so one of them is them who are empowered to issue the public-private key pair. Okay, because you have in every small place you have a post office or a postal adju office, right? So you can go ask them. I don't know what is the cost. They are authorized to give you the public-private key pair. Okay, let us go into what is public-private key pair. So what happens is, in public-private key pair, on the sender side you have a public-private key pair, and on the receiving side also you have a public-private key pair. When the sender want to send an encrypted message to the receiver, what the sender will do is, it will take the receiver's public key. Okay, the sender will take the receiver's public key. So you may ask how the sender will know the receiver's public key. Public key means, why it is called as public key means it's open, no secret. Okay, so you can put it in your email, you can put it in your website, and like in our house, we used to have, I don't know, nowadays you have or not. In my house I still have, behind my door. We call as like a cloth hanger, we have a key hanger, right? Small pins are there where you go and hang your car keys, your house keys and all that. Okay, so like that you can see there is a key hanger here. So there are websites where you can go and put your public key. Okay, so this website is like a one store, right, where all the public keys are available. You can go and register, put your public key there. I mean, both free and subscription based websites are there. Okay. Those days I used to put my public key in my email. I used to use PGP. Nowadays I don't. So I used to. So when somebody receives my email, they can see my public key at my email signature. Okay. So what happens is, so you have to listen to this carefully. That is the beauty of public-private key algorithm or public key cryptography. The sender takes the public key of the receiver. Okay, takes the public key of the receiver, encrypts the message and sends it to the receiver. Okay, and what the receiver does, receiver uses his or her private key. Why means, don't forget I said public-private key is a pair. So on the receiving side, the public key will work only with its private key. Okay, the public key will work only with its private key. Okay, that's why what the sender does is, he takes the receiver's public key, because it's open, it's known, even if it is not available in the website or blog, or in the like a key holder, it's not available. The sender can simply ask the receiver, can I know the public key? The receiver will not say no, because public is public. There's no secret. Okay, everybody in the world can know it. Okay, so using the receiver's public key, encrypts the message and sends it to the receiver. So what the receiver does, receiver uses its private key to decrypt the message. Okay, so even though the sender encrypts the message using the public key of the receiver, can the sender decrypt the message? Cannot. That's why public key cryptography is called as a one-way trapdoor function. Once encrypted, no way it can be decrypted. Just send, that's all. Okay, Just sender, that's all. Okay, one good layman example is, not layman, real-time example is your WhatsApp. Okay, WhatsApp, none of them, you can see always it says, first time you send, it always says is encrypted end-to-end. When it says encrypted end-to-end, anybody intercepts, okay, they will only read gibberish. They will not be able to read the plain text. Okay, not even the WhatsApp company. Okay, it is something like, fill it and forget it. So here, send it and forget it, that's all. Once sent, nobody can decrypt it. Okay, but there is a vulnerability here. The vulnerability is, unless the receiver leaks his or her private key. Because this public private key pair only will work. It will not work with any other pair. Okay. So now the receiver, when it wants to reply or send a message back to the sender, the receiver will use the sender's public key to encrypt the message and send it. So what the sender will do upon receiving the reply message, he or she will use his or her private key to decrypt it. Okay. So this is how public key cryptography works. Okay. One example algorithm for public key cryptography that we are going to discuss is RSA. Okay, RSA stands for the three guys who developed or who discovered this algorithm. Okay, Rivest, Shamir, and Edelman. Okay, three guys who actually developed this algorithm, and it has been named after their first name. Okay, that is RSA. So RSA, the algorithm is very simple, very simple, very straightforward. No rocket science, no complexity behind. Follow me carefully, is fun. So what RSA does is, it takes two large prime numbers P and Q. Prime numbers are those numbers that are divisible by itself and divisible by 1. Okay, those who don't know what is prime number. Okay, I know what is prime number, but what is the prime number? Sorry, I forgot. Okay, so I'm recalling it. So prime numbers are those numbers that are divisible by itself and divisible by 1. So it takes two large prime numbers P and Q. How large it is? How big it is? It is 1024 bits. So 1024 bits I cannot visualize. I'm sorry to say you cannot visualize. So what happens is, all your keyboards are ASCII keyboards. So you would have one question there giving you ASCII values in your assignment 3. That is the reason. Okay, and I think it's asking you to do encryption, decryption using RSA, and it have given some text tailors or something. I don't remember. So every time whatever comes to my mind on the fly, I just give it. Okay, sometimes I say Lakeside, sometimes I give Chomsky. The guy's name who developed the Chomsky hierarchy. Sometimes I give clean, okay, to do encryption and decryption. Let us not go there. So all your keyboard, keyboard means not your piano keyboard. I'm talking about your computer or your laptop keyboards. They follow ASCII code. Okay, ASCII is a 7-bit code. Okay, and it uses 1 bit as parity bit for error reduction and correction. Okay, so altogether it is 8 bits. So when I go and press a key here, okay, whether it is alphabet, numeral, or special character, an 8-bit value will go to the memory to be processed. Okay, so one character is 8 bits. So you can see 1024 bits means how many characters it will be, or how many digits it will be. Okay, so 1024 minimum, and so P is 1024 bits prime number, Q is 1024 bits prime number. And what the algorithm does is, in the first step, that's why I numbered. The first step, what it does is, it takes two large prime numbers, 1024 bits each, named as P and Q. It calculates N. N is the product of P and Q. You multiply P and Q, you get N. Okay, N is public, P and Q is private. Okay, why N is public and P and Q is private means, that is the beauty of this algorithm. Okay, and that is why P and Q must be minimum 1024 bits each. Okay, when you keep P and Q private, secret, you publish N. Publish N means you go and tell the whole world what N is. Knowing N, everybody knows, not everybody. Everybody who knows RSA knows that N is P by Q. N is P by Q, and P and Q are prime numbers. Okay, so knowing the value of N is public, open to everyone, known to everyone, no secret. So when N is known, can we find out what is the value of P and Q? Cannot. Why cannot means it is intractable. Now you understand why I spoke about intractable. So intractable means knowing n, can I factor n into the original value of p and q? Cannot. Impossible. Mathematically it is intractable. Okay. If you take RSA, in the lab they found out if they use p and q as 512 bits, it takes about 600-700 years to crack n into the original value of p and q in the lab. In the lab, yeah. So that hard it is, Okay. So now it calculates n p as p by q. N is public, p and q is secret, private, Okay. Then it calculates phi of n. So phi of n is equal to p minus 1 into q minus 1. Okay. And we are going to calculate or determine the public key E. E stands for encryption key. So we are going to determine what is the encryption key. So there is a formula GCD of phi of n comma E is equal to 1. Okay. We will see an example, a couple of examples, don't worry. So you will know so what we do with GCD and all that. Okay. So we have to satisfy this condition. GCD of phi of n. Phi of n is determined here. Okay. And so we have to choose the value of E, value of the encryption key, such that this formula is satisfied. Okay. And E is again public. Encryption key is again public. Okay. So once we have determined the encryption key, we determine the private key. Okay. Private key is the decryption key. Okay. So decryption key here it is labeled as D. D for Denmark. Okay. So how to determine D? D is unknown. E is known. E is known from here. And phi of n is known from here. So if we satisfy this condition or this formula, D can be determined. So we know E, we know D. Then the encryption is very straightforward. CT stands for ciphertext. So the formula for ciphertext is equal to plain text. PT stands for plain text. Okay. Plain text power E mod n. E is the encryption key and mod n. N is what we determined here, P by Q. Okay. So on the receiving side, the ciphertext can be converted into the original plain text. The formula is plain text is equal to ciphertext power D mod n. Okay. So there are a couple of examples. Actually, there are a few examples in the slides. And conscious of time, I am going to take this example, example 2. Same, but this example will be of help to do your assignment 3 as well. Because there is one similar question like this example. Okay, you are given an English plain text and you are being asked to do encryption and decryption. Okay, so in your assignment you have to just show this working. That's all. Okay. Let us take P and Q. So if you see, I have taken P as 3 and Q as 11. 3 is not 1024 bits. Okay, 11 is not 1024 bits. If you take 3, so I am writing 3 as 8 bits. Why I am writing 3 as 8 bits means ASCII. Press any key. ASCII is 7 bits, 7-bit code plus 1 bit parity bit to detect whether there are any errors or not. So altogether is 8 bits. So I'm writing 3 in terms of 8 bits. So what I'm trying to tell you guys is 3 here will be just 8 bits. It won't be 1024 bits. Then you may ask why the hell you are taking 8 bits instead of 1024 bits. We cannot take 1024 bits and do hand calculation. Okay, I can actually give you nightmare with 8 bits. Okay, if time permits, I'll show you. Okay, sometimes even 8 bits hand calculation will be bit challenging. Okay, so what we do is across the world when we teach RSA, we take small prime numbers so that we can do hand calculation. Okay, even calculation with your calculator will be difficult if you take bigger numbers. I will show you that as well. Okay, so for learning purpose and to understand how the algorithm works, we take small prime numbers, but we still take prime numbers. But it's not 1024 bits, we take 8 bits. Okay, your 11 also can be written in terms of 8 bits, right? Just 8 bits only. Okay. So we are taking two prime numbers, 8-bit prime numbers, 3 and 11, and n is 33. Okay. So now you see the beauty here. So when I say n is 33, and now you have learned n is nothing but p by q. Even I don't tell you what is p and q. I tell you what is n. You can find out. That p and q should be 3 by 11, or it should be 11 by 3. That is, p should be 3 and q should be 11, or p should be 11 and q should be 3. You can figure out easily. Okay? You can figure out easily if I tell you n is 33, because your n is very small. You understand me? That is why the algorithm takes p and q to be 1024 bits each. When it's 1024 bits each, even if you know n, you cannot find out what is the original value of p and q. It's not possible. That's why I said it's intractable. Okay. Small numbers, of course, we can find out. No, not an issue. Okay. So we calculate n as 33, p and q is 33. Then we calculate phi of n. I'm just strictly following the sequence. Then we are calculating phi of n. Phi of n is equal to p minus 1 into q minus 1. P is 3. So 3 minus 1 is 2. Q is 11. 11 minus 1 is 10. So 2 by 10 is 20. Okay. So what I am teaching you has 8 marks. What I am going to teach you later, digital signature, 8 marks. That is your question number 5 in your final exam. 5A is RSA encryption, decryption, and 5B is digital signature. 8 marks for this and 8 marks for the 16 marks. Okay. So this 40 minutes or 20 minutes you are going to spend with me, you are going to be rewarded with 16 marks. So it is up to you whether you want to have 16 marks or you don't want 16 marks. Okay. I leave it to you. So GCD, then we calculate, we are going to find E. So we know the formula to find E is GCD of phi of n comma E should be equal to 1. So we are applying that here. GCD of phi of n comma E is equal to 1. Phi of n we have already determined here. So GCD of 20 comma 3 is equal to 1. So what is GCD? Greatest common divisor. What do you mean by greatest common divisor? The biggest number, same number that divides both these numbers. It should be the biggest number. At the same time, it should divide, same number should divide both the numbers. So maybe I will show you, because I know definitely a lot of you would have forgotten what is GCD. Okay. So when we take 20 and 3, it says greatest common divisor. So the same number should commonly divide both the numbers. At the same time, it should be the biggest number. Okay. So 20 is divisible by 1, right? Yes. 3 also divisible by 1, right? Yeah. Okay. So divisible, again I have to enlighten you or make you to recall. No, whether you should recall or not. Don't worry, I understand. I'm teaching this every semester, so I remember. If I were you, I also would have forgotten. We can't remember everything that was told to us. Okay. So if you can remember everything that's been told to us, we'll go back. So our memory has been wired such way we have to forget other things. Okay. I'm just trying to recall so that you understand divisibility. Divisibility means when I divide 4 by 2, so we say 4 is divisible. Divisible. 4 is divisible by 2. 4 is divisible by 2 means 2 goes into 4 2 times. We call this as quotient. And what is the remainder? Remainder is equal to 0. Okay? So 4 is divisible by 2 means 2 goes into 4 2 times. Remainder is 0. So remainder has to be 0. That only will be divisible or divisibility. Okay? So if instead of 4 by 2, I take 5 by 2. You know, you will take, so 5 by 2 is 2.5. So 5 is divisible by 2. No. 5 can be divided by 2. It makes a difference, divided and divisible. Okay, yes? Nobody can dispute that 5 can be divided by 2, which is 2.5. Okay, but when we say divisibility, okay, 5 is not divisible by 2 because 2 goes into 5 2 times, 4, remainder is 1. Okay, remainder is 1. This also comes under modularity. Okay, modulus. The modulus has to be 0. Here the modulus is 1. 5 mod 2 is 1. You understand that? Yeah. So, 20 is divisible by 1. 1 goes to 20 times, remainder is 0. 3 also divisible by 1. Huh? Okay. So, we take 1, 1 is divides commonly both the numbers. Okay. Can we use 2? Yes. 20 is divisible by 2, but 3 is not divisible by 2. You understand? Because if you divide 3 by 2, you get remainder 1. Okay, so 3 is not divisible by 2. What else? That's all. Sorry, 2 is not divisible by 2. 3 is not divisible by 2. Can I take 3? 20 is not divisible by 3. Because 3 means 3 would go in 23, 6 or 18, remainder is 2. So 20 is not divisible by 3, but 3 is divisible by 3. But we need to have a common number that divides both the numbers. So the only common number that divides both the numbers and the biggest number is 1. You get me? Yeah. So, so GCD, that's why we put here GCD of 20 comma 3 is equal to 1. Okay? So, so what is E? So E is 3. Okay? So E is 3. So E actually can take many values, to satisfy this condition. Okay, to satisfy this condition, it can take many values. So this is a condition. So GCD of 5 of n is 20. So E can take a value 3. It will still satisfy this condition. Okay. So if you take 3, can you take 5? Can you take 4? No. 4 cannot. Does everybody understands? 4 will not satisfy this condition. Does everybody understand or not? Yes. Everybody here? Everybody. I'm hearing only few yes. I'm asking everybody in the class. Okay. One more time I explain. I know if I pull you out, I know many of you won't know. Okay. 20 can be divided by 1, divisible by 1, sorry. 4 is also divisible by 1. You can divide 20 by 1, remainder 0. Divide 4 by 1, remainder 0. Okay. So 20 is divisible by 2, 4 is also divisible by 2. Correct, right? Divisible by 3? No. 4 also is not divisible by 3. So 3 is ruled out. How about 4? Yes. So 20 is divisible by 4. 4 is also divisible by 4. So all these are the possibility. We cannot go more than 4 because this is 4 already. We cannot go more than 4 because common divisor. So the greatest common divisor of 20 comma 4 is equal to 4. The greatest common divisor of 20 comma 4 is equal to 4. But here we are not finding greatest common divisor. We are saying greatest common divisor of 20 comma E should be equal to 1. So 1 should be the greatest common divisor between these two numbers. So we have to find the number that satisfies this condition. So if you observe this E as 3 satisfies this condition, we have to see what other values will satisfy. 4 will not satisfy. 5 will not satisfy. Because just now I showed you GCD, 20, 4 is 4. GCD 20, 5 will be 5. GCD of 20, 6. What will be GCD of 20, 6? 2. Okay. 20, 7. 8 cannot. 9 can, right? 9 can or not? Cannot. Can. Already given there. So you can see there. Oh, I want to save time. So you can see there. What I want to tell you is not many materials will tell you. I'm not saying not all materials. Not many materials will tell you because they think it is understood. Okay. So I'm explicitly telling you that's all. Okay. So E can take many values that will satisfy this condition. Okay. So what I do is I take the smallest value that satisfies this condition. You may ask why you're taking the smallest value. Again, I'm using hand calculation, easy for me. Okay. So why it is easy for me, you will come to understand shortly. Okay. So E can be 3, E can be 7, 9, 11, 13, 17, 19. Okay. So I'm taking E as 3 here. So E can take any of these values. Okay. So the maximum value of E will be less than phi of n. Okay. It will always be less than phi of n. Huh? Okay. Now once we have found E, what is next we have to find? We have to find D. So to find D, we already have a formula. I also written here. D into E mod phi of n is equal to 1. Okay. So E is known, phi of n is known. What is E? We just took E as 3. Okay. Phi of n is 20. So 3D mod 20 is equal to 1. So we have to find out the value of D such that it satisfies this condition. Okay. To me, this value should be multiples of 20 plus 1 because 21 mod 20 is equal to 1. 21 mod 20 is equal to 1. 41 mod 20 is equal to 1. 61 mod 20 is equal to 1. 81 mod 20 is equal to 1. 101 mod 20 is equal to 1. Mod is same as division. Okay. Mod is same as division. For example, 5 divided by 2, 2 goes into now division, not divisibility. Okay. 5 divided by 2, 2 goes into 5 2 times. We call this as quotient. And we have remainder 1. Okay. So a difference between division, not divisibility, difference between division and mod is, in division we give importance to quotient. Okay. In mod, quotient is ignored, only remainder is taken. So for example, I can rewrite this: 5 mod 2 is equal to 1. Because we basically divide 5 by 2 and we take the remainder. Okay, we basically divide 5 by 2, we take the remainder, that is 1. Okay, so that's why I said this value will always be a multiple of this value plus 1. Because 21 mod 20 is equal to 1, 41 mod 20 is equal to 1, 61 mod 20 is equal to 1, 81 mod 20 is equal to 1. Okay. So when we say 21 mod 20 is equal to 1, what multiplied by 3 will give you 21? The answer is known already. This is what beautifully in English we say trivial. This problem is trivial. Okay, 3D mod 20 is equal to 1. This problem is trivial, meaning solution is visible already in Malaysian slang. Okay, solution is visible already because we know 21 mod 20 is equal to 1. So D should be 7 because E is known, 3 is known. 3 sounds are 21. So 21 mod 20 is equal to 1. So D should be 7. So once we know E and D, we just apply the formula here. We can do the encryption and decryption. So here the name Susanna is given, and these not ASCII values. Okay, this actually is taken from a textbook, Andrew S. Tannenbaum, Computer Networks. So this is a sequence number. A is 1, B is 2, C is 3, D is 4. So you just take the sequence number. So in sequence, S is 19th alphabet. Okay. So U is 21st alphabet. You can see Z 26th last alphabet. So these are simply sequence numbers. Okay. Just to understand the concept, your computer doesn't use sequence number, computer uses ASCII values. Okay. That's why in assignment I would have given the ASCII table. So that for every text you have to take the ASCII value, convert it to binary. Because usually ASCII value will be in hexadecimal. You have to convert it into binary, and then you have to convert it into decimal like this, and then you have to do the calculation. Okay? So S is, the numerical value is 19. So 19 is your plain text. Okay? The numerical value of the alphabet, yes. Okay? So 19 is the plain text. Power E mod n. What is E? E is 3. Okay? So 19 power 3 mod 19, the formula is given here. 19 power 3 mod n is 33. So 19 power 3 mod 33. Power 3 mod 33. 28. And you can see that's what you're seeing, 28. Okay? On the receiving side, 28 will be received. Now it has to be converted to plain text on the receiving side. So what is the formula to convert ciphertext to plain text? Ciphertext power D mod n. Ciphertext is 28 and D is 7. So 28 power 7 mod 33. We should get back the original plain text. So 28 power 7 mod 33. 19. Yeah, 19. You got back your original numerical value. So meaning you got back your original text, yes. So you do this for all the remaining alphabets. So I don't know whether it is question number 3 or not. I am not very sure. It is one of the question in your assignment 3. So you just show this table and this calculation and this table good enough. You put whatever text is there, Taylor's or whatever it is there, Alan Turing, I don't know what was the text I gave. You put the text here, put the numerical value, put the cipher text value, then again numerical value and the original plain text, done. That's all done. It will take only 5 minutes. That's why I said, once you learn this, your assignment 3 is not going to take much time, maybe an hour, 1 hour. You are going to do in group anyway. Only time it will take is that 5-page essay on, digital signatures. Okay? So what is the awareness of digital signatures and all that? Today the awareness is very big. 2 years back, the awareness was not much. Okay? All right. So one more. Oh, 5 minutes. Okay. Let me take attendance. Please tolerate me for 2 minutes because digital signature will take only 2 minutes because you already learned RSA. You just apply the formula, but we are going to make a small tweak to the application of the formula, and then you get digital signature. Then RSA is over. So we can do tutorials in the next class. Okay? So let me open cams and just stay with me. Those who want to leave can leave, no issue. But I request you to just stay for, at the worst case, 5 minutes. Reminder. So once I go home, I also will remind you through my times. This Saturday is your assignment 2 submission. I saw today morning there were only 5 submissions. There should be another 25-30 more. Okay. So please be reminded. I will send a reminder. Just refresh, it will work. Working? Anything here? We don't have any access privilege to this system. Okay? None of the lecturers, PD. After you mark, I cannot even go and check whether you have marked at. And please tolerate me for some time. Definitely, you will get your coursework mark before you go for exam. Coursework means entire marks for all the assessments. So probably by end of next week, I will try to give you back your test papers marked, and after that, your assignment 2. Okay? Yeah. Because it will take a lot of time to mark. It's not tick, 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 tick. Yeah. So you have to tolerate me a bit. Please tolerate me. I'll give you back your test papers marked. I will also discuss the answer. All taken? Okay, jumping back to digital signatures. See, we are just going to make a small tweak to the formula. Here in RSA encryption, decryption, to do encryption, we use the formula cipher text is equal to plain text power E mod n. Okay, for encryption, we use ciphertext equal to plain text power E mod and write.